Welcome to the Two Beans in a Pod by Jamie and Haley. Today we're embarking on, a really fascinating exploration. It's something that sounds a bit like science fiction, but it's absolutely fundamental to our reality. We're talking about the Earth's magnetic pole shift. You sent us some incredible sources on this, and our mission for this deep dive is to really get our heads around what's happening with our planet's invisible magnetic field.
Yeah, how it's moving, what's actually driving these shifts.
Exactly, and the surprising kind of real-world implications this has for everything from, how we navigate the globe,
right,
to maybe even the ground we stand on.
Yeah.
It's pretty wild stuff.
It really is. It's a truly captivating journey, kind of peeling back the layers on this invisible shield that envelops us, and how even seemingly subtle changes within it can have these cascading, far-reaching effects.
Right.
We'll definitely delve into why this movement matters, connecting some, seemingly disparate dots.
Like what?
Well, between the churning molten iron deep in Earth's core, the unexpected influence of human engineering.
Human engineering. Okay, interesting.
And even recent seismic activity. Yeah, prepare to see our planet in a whole new light, perhaps.
All right, let's do it. Let's unravel this mystery.
Yeah.
So when we talk about the Earth's magnetic pole, it's important to clarify, isn't it? It's not the same as the geographic North Pole.
That's a key distinction, absolutely.
The geographic North Pole is like the fixed point, right? Where the planet's rotational axis pokes out the top.
Yeah.
That's your unchanging spot.
Correct, like the top of a spinning top.
But the magnetic North Pole, that's a different beast altogether. It's a dynamic, moving target. It's the ever-changing location where Earth's magnetic field lines actually converge, the place that compass needle points. It's definitely not static.
Exactly. And that magnetic field, that shield we mentioned, it isn't some external force acting on us. It's generated from within.
Right, deep down.
By what scientists pretty cleverly call the geodynamo.
Geodynamo, okay.
Yeah, try picturing this. Nearly 1,800 miles beneath our feet, deep inside Earth's outer core. There's this colossal churning ocean of molten iron and nickel, just incredibly hot liquid metal.
Wow.
And as it swirls and flows, driven by convection currents and the Earth's rotation, it generates electric currents.
Okay.
And those electric currents, in turn, produce our planet's magnetic field. So the reason the magnetic pole shifts is because the fluid dynamics of this deep-seated engine are constantly changing.
So it's alive, in a way.
It's a dynamic internal process, yeah, a living part of our planet.
That's absolutely mind-bending to visualize. So this magnetic North Pole, it was first officially located when?
Back in 1831 by the explorer James Clark Ross.
1831. And for a long time after that, it just seemed to be kind of gradually shifting across the Canadian Arctic, almost lazily.
Right. For many decades, it did seem relatively stable, just a slow drift. But its recent movements, anything but lazy.
Okay.
Over the past century, its journey from northern Canada towards Siberia has really picked up pace significantly.
How much pace?
Well, for decades, it drifted at maybe 6 miles per year. Pretty modest. But by the 2000s, that speed had dramatically accelerated. It peaked at around 31 miles annually.
31 miles a year. That's a huge jump.
It's a significant acceleration for something on a planetary scale like this.
And here's where it gets even weirder, right? Because in just the last 5 years, that rapid speed has actually slowed down quite a bit.
Exactly. It's decelerated significantly down to about 22 miles per year.
22. Still fast, but much slower than 31.
William Brown from the British Geological Survey actually called this the biggest deceleration in speed we've ever seen.
Wow.
So it's not just moving, but its rate of movement is also changing dramatically. It's almost like, well, like you said, a living thing deciding to speed up or slow down.
It really makes you wonder why. What's causing these changes in speed?
That's the multi-million-dollar question. And that change in speed, especially the recent deceleration, has very real, tangible implications.
Okay, like what?
Well, think about global industries. Aviation, shipping, the military.
Right, navigation.
They absolutely rely on highly accurate, really up-to-the-minute models of this magnetic field for all their navigation systems.
So every GPS, every plane, every ship, they're tracking this constantly.
Precisely. They need to know exactly where that magnetic North Pole is at any given moment because essentially it's their guiding star.
Which brings us to the World Magnetic Model, the WMM.
Exactly.
This isn't just some scientific curiosity then, it's a vital tool.
Absolutely critical. British and American scientists work together on this, releasing a new updated edition every 5 years.
And the latest one, just out in December, confirms the pole is now definitely closer to Siberia.
That's right. The trend continues, even with the slowdown,
Right.
closer to Siberia than it was 5 years ago.
And the precision needed for these models, it's pretty intense, I imagine.
Oh, it cannot be overstated. The longer they wait to update that model, the larger the error builds up in navigation systems. There's a really striking example they use.
Yeah.
Imagine you're trying to travel, say, 5,280 miles in a straight line, maybe South Africa to the UK.
Okay.
If you were relying on an outdated WMM, you could end up a staggering 93 miles off course.
93 miles.
Yeah,
Wow.
that's
You'd miss your destination entirely.
You could end up in the wrong country, or worse, the middle of the ocean.
Yeah.
It really highlights how critical these updates are for safety and, efficiency on a global scale.
And what's really fascinating here, you touched on it earlier, is that scientists are still largely unsure why the speed changed so dramatically, why the acceleration, and now why the deceleration.
Right. It's a complex puzzle. Some researchers hypothesize that the magnetic field might be getting weaker over Canada,
Okay.
but at the same time, it's growing stronger over Siberia. And that could be creating a kind of magnetic tug of war, pulling the pole towards Siberia.
Magnetic pole.
Sort of. But overall, they describe the field's behavior as incredibly complicated and even chaotic.
Chaotic. That doesn't sound reassuring for modeling.
Well, it certainly highlights why the WMM needs such frequent updates. It's a potent reminder that even with all our advanced tech, parts of our own planet remain profoundly mysterious.
Absolutely.
Yeah.
Now, you mentioned something earlier that really caught my ear. Human engineering. How do humans fit into this picture of planetary magnetic shifts?
Yeah, this is perhaps one of the most surprising connections. When we talk about pole shifts, we usually think purely natural geological stuff, right?
Earth processes, yeah.
But new research is showing an astonishingly direct human contribution. It's the sheer amount of water that humanity has dammed up behind walls all around the globe.
Wait, dams. The water in dams has shifted the Earth's axis. Seriously.
It sounds incredible, I know, but we're talking about the cumulative mass of water concentrated in just under 7,000 of Earth's biggest dams.
Okay.
Researchers have calculated that this incredible weight, this redistributed mass, has literally nudged the crust's axis of rotation off kilter.
By
By about 1 meter, or roughly 3 feet, relative to that deep dynamo generating the magnetic field.
Wow. 3 feet. That's
Yeah.
measurable. A direct human impact on the planet's spin.
It is. It's not just a subtle effect. Think of it like this. The Earth's magnetic field generator, that geodynamo, is deep down, right?
Mm-hmm.
This phenomenon, called true polar wander, isn't the deep engine moving. It's more like the Earth's surface. The skin of the Earth is subtly reorienting itself around that inner engine.
Because of the weight distribution.
Exactly. The immense weight of water in these reservoirs subtly pulls the Earth's crust towards the equator, effectively tilting the Earth's spin axis relative to that deep magnetic core.
And we can actually see this in the historical data?
We can. It's quite amazing. From around 1835 to 1954, the North Pole shifted eastward by about 20 centimeters.
Okay.
That period lines up pretty well with when major dams were being built mainly in Europe and North America.
Right.
Then, between 1954 and 2011, it moved a more significant 57 centimeters, but this time west.
And that corresponds to?
That correlates really well with the huge boom in dam construction across Asia and East Africa.
That's incredible. A direct, almost real-time illustration of our impact.
It really is. And this global water hoarding, it doesn't just influence the pole's position, it also connects to broader planetary changes, including potentially our weather.
How so? Weather?
Well, this mass redistribution of water behind dams has actually, somewhat paradoxically, caused a tiny drop in global sea levels, about 21 millimeters overall.
A drop. Because the water's trapped on land.
Exactly. It's trapping about 1.2 millimeters per year of potential sea level rise on land. Now, while that might sound, good in one sense.
Right. Let sea level rise sounds okay.
But it also fundamentally changes the geometry of global sea level rise, where the water is and where it isn't. This redistribution of mass can subtly alter things like large-scale ocean currents and atmospheric patterns.
Potentially influencing storms.
It's possible it could influence the intensity and pathways of storms, though the exact mechanisms are still being actively researched. It just highlights how interconnected everything is.
It really does.
And we shouldn't forget, the magnetic field itself plays a role in shielding us and funneling energy from solar winds, space weather. That's another layer of complexity when we think about Earth's energy budget and atmospheric impacts.
It's truly mind-blowing to think about how all these forces intertwine, isn't it? We've only just scratched the surface here. Okay, let's just pause here for a moment. If you're finding this deep dive as fascinating as we are, and you want to keep uncovering these kinds of planetary secrets with us, please do take a second to hit that like button and subscribe right here to the deep dive.
Yeah, your support really does help us keep bringing these unique insights directly to you.
Okay, so we've talked about the wandering pole, the models, the human impact through dams. Now let's pivot to something else quite compelling. Recent earthquakes and some really strange magnetic pulses.
Right, this is another area where things get, well, interesting and a bit mysterious.
Specifically, we're looking at Alaska, right?
Yeah.
A magnitude 7.3 earthquake back on July 16th, and then a 6.2 aftershock a few days later, July 20th, near Sandpoint.
And what was observed by the Shumagon Magnetic Observatory, which is basically sitting right on top of this earthquake zone, is really remarkable.
What did they see?
These powerful earthquakes seem to be accompanied by what looked like massive magnetic pulses, huge, very rapid shifts in the local magnetic field strength.
Massive owl. Like, what does the data show?
Yeah.
Because the field fluctuates normally, right?
It does, but usually in the tens, maybe hundreds of nanotesla range over a day.
Okay.
Here, the first pulse showed maybe 140 nanotesla change in the vertical component noticeable, but okay. But then these absolutely huge shifts in the horizontal components, 7,000 nanotesla in one direction and 2,300 nanotesla in the other.
7,000, compared to hundreds normally.
Exactly, orders of magnitude larger. And the second pulse from the aftershock showed similar corresponding spikes. These are not minor blips.
Wow. So what could cause that?
Well, that raises a really important question for the scientific community. Are these hyper-localized, massive magnetic field changes actually happening during big earthquakes? Is this a real physical phenomenon that's just never been properly documented before?
Something completely new about earthquakes and magnetism.
Potentially. Something never reported on in the literature, as they say. Or a niche change. Could it be something more mundane, like an equipment issue?
Like the sensor malfunctioning during the shaking.
Or maybe a sensor being too close to some metal that got moved or stressed during the quake, causing a false reading. Both possibilities, the extraordinary and the, well, less extraordinary, are on the table. Scientists are trying hard to figure it out.
But either way, it's highly unusual and needs explaining.
Definitely.
It makes you wonder, is there some connection between the overall magnetic pole shift happening up in the northern hemisphere, that rapid movement we talk about, and these sudden localized magnetic jolts during earthquakes?
That's the big question, isn't it? If these pulses are confirmed as real, widespread phenomena, wow. It opens up entirely new ways to think about how Earth's deep processes, magnetism, and seismic events interact.
It could potentially change how we monitor, maybe even predict earthquakes down the line?
It's possible. It's a profound mystery. Scientists are clearly very keen to unravel right now.
Okay, so connecting all these dots, the wandering pole, the human impact, these strange earthquake signals.
Yeah.
What's the bigger picture? You mentioned the field weakening overall.
Right. If we zoom out, the Earth's overall magnetic field strength is actually weakened by about 9% over the last couple of centuries.
9%, that sounds like quite a bit.
It is noticeable, and this has naturally led to some speculation about a potential geomagnetic reversal.
Where the poles flip,
Yeah.
north becomes south, south becomes north.
Exactly. It sounds incredibly dramatic, and it would be a major event, but it's a natural planetary process. It's happened many times in Earth's history.
When was the last time?
The last full reversal was around 780,000 years ago.
Okay, so quite a while back. Are we due for one?
That's the thing. Despite the weakening field, scientists honestly cannot predict when the next reversal might happen. It could be thousands of years away, or, well, we just don't know if this current weakening is a definite prelude to one happening anytime soon.
Right. So, wrapping this up, what does all this mean for us living on this clearly very dynamic planet?
Well, the main takeaway is probably that while a full pole reversal isn't expected imminently,
Okay, good.
and the magnetic North Pole's recent frantic movement has actually slowed down a bit, the future is still really uncertain.
It could speed up again, change direction.
It could change its rate, speed up, maybe even reverse course briefly. We don't fully understand the driver well enough to predict its next move accurately long term.
It's a powerful reminder, isn't it, of our planet's incredible, ever-changing nature and how much we still have to learn about these hidden forces shaping our world.
Absolutely. And this whole discussion, from the molten core to the water we dam up to the ground shaking beneath us, it kind of raises an important question maybe for you to think about after this deep dive.
Okay?
As we keep uncovering more and more about our dynamic planet, about these powerful, unseen natural forces, what new responsibilities do we gain as inhabitants, How should we understand, adapt to, and maybe interact with these profound planetary systems?
That's a great question to ponder. Understanding brings responsibility.
Something like that.
Well, we really hope this deep dive has given you a whole new perspective on our planet's incredible hidden forces and the, frankly, mind-bending science behind them. Before you go, if you enjoyed this and haven't already, please do hit that like button and subscribe. It genuinely helps us continue to bring these unique deep dives to you.
It really does. Thanks for tuning in.
Thank you for listening to Two Beings in a Pod.